Hello everyone and welcome back. My name is Mr. Kovalt and in this video we're going to be going over specific heat. Okay, well what is specific heat or specific heat capacity as it is often called? Well, specific heat is the amount of energy it takes to raise the temperature of 1 gram of some substance by 1 degree Celsius. And so the units for that is going to be based on that definition, the amount of energy in joules, and that's usually measured in joules or kilojoules, but for specific heat capacity, it's usually going to be in joules. And then per gram per degree Celsius. So it's the amount of energy that it takes to raise the temperature of 1 gram of something per by 1 degree Celsius. So that's where we get the joules per gram per degree Celsius. Okay, so that's the specific heat, and we can use specific heat to calculate the amount of heat or energy that's either absorbed or released by that object. So if we know how much heat is gained or lost by a substance per degree per gram, then if we want to find the amount of energy that is absorbed by that substance, the total amount of energy absorbed by that substance, then we would need to know the mass, right? Because we need to know the gram amount, and we would need to know the temperature change, or how much temperature, how much degrees is changing. So if we know that, then we can get the equation. So if I just want to know the heat or the energy, what I can do is, well, since I know heat capacity is joules per gram per degree Celsius, and I know that energy is measured in joules, and I want to know how much energy was absorbed or released by this particular object, then according to this, I would have to get rid of the grams in the units of heat capacity or specific heat capacity and the unit of degrees Celsius. And how do I do that? Well, since grams and degrees Celsius are on the bottom here, then I would have to multiply by grams and I would have to multiply by degrees Celsius. And in this case, I would have to multiply by a change in temperature, which would give me degrees Celsius. So if I multiply by the mass and the temperature change, then I can get joules by itself, and I have the amount of heat that's either absorbed or lost by the object. So that brings me to this equation here. So this is a very well-known equation in thermodynamics. So the amount of heat is Q, quantity of heat. So the quantity of heat that's either absorbed or lost is equal to M, which is the mass, times C, which is the heat capacity, times delta T. Now, delta is often used to refer to change. So the change in temperature, and change in something is usually going to be final minus the initial. So here, this is the final temperature minus the initial temperature. So this is often referred to as Q equals MCAT. And for those pre-med students out there, you know what the MCAT is, that exam you take to get into med school. So Q equals MCAT. Okay, so again, C is the specific heat that we have the units here for. Q is the energy lost or gained by the object. And the M is the mass in grams. It's got to be in grams because heat capacity is often in grams. Now, heat capacity, or I should say specific heat capacity, is not always in grams and joules, but it can be. It can also be in moles sometimes. So you got to pay attention to the units, because the units are going to determine what you need to multiply by to get the energy, right? So if this is in moles, then I need to multiply by moles. But usually it's in grams. And then we have the delta T, which is the change in temperature. And again, change in temperature is going to be the final temperature minus the initial temperature. So we put that together again. Q is equal to mass times the specific heat times the change in temperature, which is TF minus TI, final minus initial. Okay, so one thing you want to keep in mind that's it's going to be a simple trick for you, and it's going to save you a little bit of calculations, is um, delta T in kelvins is the same as delta T in Celsius. So if they give you temperature in Kelvin, and notice you have to have degrees Celsius here, then you would have to convert Kelvin to Celsius, but you don't have to, because remember, in a previous video, I talked about the difference and similarities between the different temperature scales. And one thing we noticed about Kelvin and the Celsius scale is that the degrees of Celsius and the increments of Kelvin are equal. They are equal in size. So 1 degree Celsius is the same as one increment of your Kelvin scale. So that's why when to convert from Celsius to Kelvin or Kelvin to Celsius, you all you need to do is add or subtract a certain number. So 273.15, right? So you either add 273.15 or you subtract 273.15 from either Celsius or Kelvin, depending on which way you are converting. And the reason for that is because they have the same size. The increments are the same size. Not unlike the Fahrenheit scale where the increments are different in size. And that's why in order to convert from one to the other, not only do you have to subtract or add 32 degrees, but you have to multiply by a factor of the size difference, right? Which is usually something like 1.8 or the inverse of that. Or 5/9 or 9/5, depending on which way you are converting. So, but in this case, since the Kelvin scale and the Celsius scale have the same size increments, so finding the difference in the temperature in Kelvin is the same as finding the difference in the temperature in Celsius. So if they give you the change in temperature in Kelvin, just find the difference in Kelvin and it'll be the same as the difference in degrees Celsius. So that might save you some calculations. Okay. Finally, I want to talk about exothermic and endothermic processes or reactions. So here again, both mass and specific heat are going to be positive. So the whether Q, the quantity of heat absorbed or released, is positive or negative, is going to be dependent upon the temperature change, right? And so if the temperature change is positive, meaning that the final temperature is larger than the initial temperature, then that means that the Q value, the quantity of heat, is positive. And these positive or negative values mean something. So here, because the temperature change is positive, meaning that you end up with a higher temperature of the object than you started with, right? So the final temperature is higher than the initial temperature. That means that the object absorbed energy, right? You absorbed energy, the temperature goes up. And so if the temperature goes up, it absorbs energy and therefore Q is positive. So whenever Q is positive, that means your object is absorbing energy, and therefore it's called endothermic. Therm refers to heat. That's the Greek for heat, thermos. That's where we get the word thermos from, right? That keeps our coffee hot in the morning, right? So thermic, and endo means into, going into, right? So endothermic, heat is going into, heat is being absorbed, right? So the object is absorbing heat. And then if the delta T or change in temperature is negative, that means that the final temperature was lower than the initial temperature. So when you subtract the final from the initial, you get a negative value. It's a negative change. So that means that the object is losing energy, right? It's decreasing in heat, it's decreasing in temperature, I should say, and therefore that's indicative of losing heat. And so delta T will be negative, and therefore Q will be negative. And in that case, it's exothermic. Again, therm referring to heat, and exo meaning out of, going out of. So exothermic means that heat is going out of the object or system. And so that's the next thing I want to kind of stress here is we're viewing this from the perspective of the system and not the surroundings. So unless told otherwise, you're viewing these processes from the system's perspective. And the system is going to be either usually the chemical reaction or the object of focus, whatever that object is. It could be a block of metal or something, or it could be a reaction in a solution or something like that. So, but it's always viewed from the system's perspective. So, if the system is gaining heat, then that means the surroundings is losing heat, and we're assuming that it's the same amount that's being lost and gained, right? So we're thinking about the first law of or the second law of thermodynamics, where energy is conserved. Okay, so that's it for this part of the video. So next, I'm just going to go over a few practice problems. So stay tuned. Okay, welcome back. So here's example problem number 1. How do we use this equation to help us solve problems? And again, the equation we're using is Q equals MCAT, mass times the specific heat times the change in temperature. And remember, change in temperature is T final minus T initial. Okay, so our first problem is how much heat is needed to raise the temperature of 10 grams of a substance from 40 degrees Celsius to 60 degrees Celsius if the specific heat is 3.8 joules per gram per degree Celsius. So the way we're going to do this is we have our equation, and we want to list the information we're given and label it so we know what we need to find. So here we're given the mass. The mass is 10 grams, so that's M. So M is equal to 10 grams. We're given that we're heating the substance from 40 degrees to 60 degrees. So our initial temperature is 40, and our final temperature is 60. So our delta T is equal to final temperature minus initial temperature, which is equal, what's our final? Is 60 degrees. So 60 degrees minus the initial temperature, which is 40 degrees Celsius. And then we find that difference, and it's going to be 20 degrees Celsius. So that's our change in temperature. And finally, they give us the specific heat. So the specific heat, again, is C, capital C, which is equal to 3.8 joules per gram degree Celsius. And what are they asking for? So remember, when you're dealing with these type of problems like word problems, especially in chemistry or science or maybe even math, you find the conversion factors in the problem, or you find the information they're giving you in the problem, and you figure out what they're asking for. Remember, the end of the problem is at the beginning of the question. So you got to go to the question to get to the end of the problem, and a lot of times the beginning of the problem. So you want to know where to begin and where to start. And in this case, the question is saying how much heat. So the heat is what we want. Remember, Q is heat. So Q is what we're looking for. How much heat? Okay, so, and we're talking about raising the temperature. So if we're raising the temperature of something, then that indicates that that thing is going to be absorbing heat. And so we should expect Q to be positive. So let's find out. So we're going to take our values here. We're going to plug them into our Q equals MCAT equation. So Q is equal to, and you should always write the units down in your equation so you can make sure all the units cancel out and you're left with the unit you want. So Q is equal to the mass, so we have 10 grams. So 10 grams multiplied by the specific heat, which is 3.8 joules per gram degree Celsius, multiplied by the temperature change, which is 20 degrees Celsius. So you can see here that the grams cancel out, degrees Celsius cancel out, and I'm left with joules. That makes sense because joules is an energy unit. I'm looking for heat, which is energy. My light went out again. So I have an energy unit. I'm looking for heat. It works out. So now all I need to do is calculate, and the answer I get is Q is equal to 760 joules of heat. So notice it's positive, which is what we expected, and so we did this problem right. So that's the first example problem. Let's do the next example. Okay, welcome back. So here's example problem number 2. A 2-gram sample of a metal was heated from 260 Kelvin to 300 Kelvin. It absorbed 52 joules of heat. What is the specific heat capacity, or what is the specific heat? So let's pull out the information they give us and label it. So we have a 2-gram sample. So 2 grams is the mass. So the mass of the sample, M, is equal to 2 grams. Okay, so what's next? So this 2-gram sample of metal was heated from 260 to 300. So it's gaining heat. So that allows us to find the change in temperature. Remember, we want specific heat to have degrees Celsius in it. So in this case, remember that the change in the Kelvin temperature is the same as the change in degrees Celsius. So it's the same. So you don't need to convert this degrees Celsius and then do the change, because the units are the same size. So we can just find the difference here. So delta T, again, is going to be temperature final minus the initial temperature. The final temperature here is 300 minus 260. And so the difference here is 40 Kelvin, which is the same as 40 degrees Celsius. So this same difference. Okay, so remember, this is the change in temperature, not the absolute, not the temperature itself. Okay, and then we're told that it absorbed 52 joules of energy. That's our Q, right? The amount of energy absorbed or lost is the Q value. So Q in this case is a positive 52 joules, because we're told it absorbed energy, and when the object absorbs energy, it's gaining energy, and that's a positive thing. It's gaining, so positive. And so we got our information, and then the question is, what is the specific heat? So that's what we're looking for. That's what we want. So capital C is a question mark. So you can either solve your equation for the missing part. So you could solve your equation for C and then plug in your values, or you can plug in your values here and then solve for C. It's up to you. It doesn't really matter. So let's just plug in our values, and then we can solve for C. So here we have Q. So Q is equal to 52, so it is equal to a positive 52 joules. Here, let me write the equation first and then plug things in. So Q is equal to mass times C times delta T. So Q is going to be 52 joules positive equals the mass, which is 2, times C, which is what we're looking for, times the change in temperature, which is 40 degrees Celsius. So all we need to do is solve for C. So we divide, we can multiply these together. So, oh, I forgot we should have our units in here. So this is grams, this is degrees Celsius, this is joules. And remember, when we solve this, heat capacity should have the units of joules over degrees Celsius and grams. So when we multiply this together, we get 80 gram degrees Celsius multiplied by the specific heat. That's going to be equal to 52 joules. Then you divide both sides by 80 gram degrees Celsius. 80 grams degrees Celsius. That cancels out. And then you end up with, what did I calculate to be? 0.065. So the heat capacity for this unknown metal is 0.65 joules per gram degrees Celsius. And so you can see that I've got the units of specific heat, which is what I wanted. So the units match what I want. So that's good. So here is our answer. Okay, that is example problem number 2. Let's go on to example problem number 3. Okay, so example number 3. So the only difference between the last example and this example is instead of having Kelvin temperature, we converted those, or we're given them in degrees Celsius, and we'll see if it works out the same way. So again, let's write out what we have. Again, we have mass is equal to 2 grams. Okay, and now the temperature change is delta T, and it's final minus initial. So in this case, the final temperature is 27 degrees, which is the same as 300 degrees as we had before, 300 Kelvin as we had before. So we have 27 degrees Celsius, and we're going to subtract the initial temperature. Now here, the initial temperature is negative, so you got to be careful with those double negatives. So we're going to subtract out the negative 13 degrees Celsius. And so when you subtract a negative, that becomes positive. So you're going to add these together. So this becomes 27 degrees Celsius plus 13 degrees Celsius, and that becomes 40 degrees Celsius difference. So last time we had a 40 Kelvin difference. This time, same exact temperatures, but now in a different scale, but you get the same difference. So it's just to show that the difference in Kelvin is going to be the same as the difference in degrees Celsius. And then, of course, our Q value again is equal to a positive 52 joules because we're absorbing energy. Plug this in. Now this time I'm going to solve the equation first for C. So here, when you solve for C, you're going to divide both sides by M and delta T, and you get Q over M over delta T. So that's going to be C is equal to Q over mass times the change in temperature. So now we can just plug in our values. So here Q is going to be 52 joules over the mass, which is 2 grams. So we have 2 grams multiplied, and on the bottom we have this delta T here. So delta T is 40 degrees Celsius, 40 degrees Celsius. And we do the calculation again, and once again we get 0.65 joules per gram degrees Celsius. So there's our answer again. So either way, it doesn't matter if you use a Kelvin difference or a degree Celsius difference, you get the same answer. Okay, what about our next example problem? Hold on, I'm glad you asked. Okay, here we are with example problem number 4. We're given a 50-gram piece of a hot metal, and it is put into cold water. So we're going to get a heat transfer from the hot metal to the cold water, because that's the way that heat gets transferred. It goes from a higher concentration to a lower concentration. So it's going to go from the hotter object to the colder object, or the hotter side to the colder side. So here, when you put the hot piece of metal into the cold water, the heat is going to transfer from the hot metal to the cold water, and it tells us that it transfers 5,000 joules of energy to the cold water. Gives us the specific heat of the metal, which is 6 joules per gram per degree Celsius. And they're asking, what is the change in temperature of the metal? So now we're looking for change in the metal. Now, notice or ask yourself, where is this energy going? It's going to the water. Now, they could have easily asked us, what's the temperature change of the water? But they didn't give us any information about the water outside of the fact that it's absorbing 5,000 joules of energy. We would need to know the heat capacity, or that we would need to know the specific heat capacity of water. We wouldn't have to know what mass of water is absorbing that amount of heat. And they don't give us that, so that's not what we're going to be looking for. And they don't ask for that. They ask for the metal, which we do have the information, right? So we know it's 50 grams, so the mass is equal to 50 grams. And we know that it's transferring 5,000 joules to the water. So our system that we are considering is the metal, the piece of metal itself. So it's transferring, the piece of metal is transferring 5,000 joules to the water. So it's losing that heat. So this is negative. So this is our Q value, the amount of energy lost. So Q here is equal to a negative 5,000 joules. And they give us our specific heat. So the specific heat is 6 joules per gram degree Celsius. So we need to find delta T, which is the change in temperature. What's our delta T? So let's go ahead and solve our equations for delta T. So we have Q is equal to mass times C delta T MCAT. If we divide both sides by M and C, so that means our delta T is equal to Q over MC. So here, now all we need to do is plug in our values. Q is negative 5,000, so negative 5,000 joules. Our mass is, where's our mass? 50 grams. And our heat capacity, or specific heat, I should say, is 6 joules per gram per degree Celsius. So we have 6 joules per gram degrees Celsius. And so we can see that joules cancels out. We have joules on top and bottom. Here we have grams top and bottom. And so we're left with 1 over degrees Celsius. So 1 over degrees Celsius in the denominator is flipped to give us degrees Celsius in the numerator. So we have our degrees Celsius. So we plug this in and we do our calculation, and we come with our delta T is negative 16.67 degrees Celsius. So you can see that our delta T is negative, meaning that there is a temperature change such that the block itself, it's transferring heat, so it must have decreased in temperature because it's losing heat. So it went from a high temperature to a low temperature. And so when you do the final minus initial, your final temperature is lower than your initial temperature. So when you subtract them, you get a negative value. So we have a negative change in our temperature. So that means that it decreased in temperature, which is what we'd expect if you're transferring heat out. So That is the answer. So, one more problem, shall we?